Okay, here we go with the dot diagrams section of the final review. So the first thing you need to do on number 19 through 20 is to fill in the blanks. So for the dot diagram for SO2, which is sulfur dioxide, we need to find out how many valence electrons there are. So to do that, you need a periodic table. So let me pull this thing in. And if we click on our periodic table, we can see these rows. Remember, the number of valence electrons depend on the column. Everything in this column has 1. Everything in this column has 2. Then continuing on with the next tall column, it has 3, and then 4, 5, 6, 7, and then 8. So you notice that sulfur is in the 6th column. You can also go by the Roman numerals. See, that's a VI, which means 6. So 6th column has 6 valence electrons. Oxygen's also in the 6th column and has 6 valence electrons. So the sulfur has 6 and the oxygen has 6. So really you're looking at 6 plus 6 plus 6. And once again, that was for the sulfur having 6 and each oxygen having 6. So our total number of valence electrons is how many? Looks like 18. So we got 18 valence electrons. Now if you go back to the periodic table, you can see that the element that's closer to the middle between sulfur and oxygen is sulfur. So the element close to the middle is sulfur. Now the next thing you need to do is draw the skeleton structure. You'll notice I have this little sheet over here in the background. This was what I used to teach you how to do it when we were doing notes. So the skeleton structure would have sulfur in the middle, and then you'd have O's attached on the outside, because remember, sulfur was closer to the middle of the periodic table. If you go over and look at the rules, it says also could be the element with the most bonding sites. Well, in this case, they all had the same because they had 6 electrons. Each one of them has 2 open spots because they could have 8. So there's room for 2 more. So there are 2 open spots or bonding sites. The third thing is the least electronegative is another thing to consider. So if we wanted to consider that, we could go look at the electronegativity chart, which is right here. And between oxygen and sulfur, you see sulfur is less electronegative. So let's pull this out of our way. Pull this out of our way. And maybe I can leave that there. Pull this up. Actually, pull this over. Hang on just a minute. I'm rearranging all my windows. All right, so now we're going to draw our skeleton structure. We've got sulfur in the middle. We have sulfur on the outside, or sulfur in the middle, and oxygen's on the outside. All right, so now you subtract 2 electrons per bond from the total number of valence electrons. So how many bonds do we have? 2. So the number you need to subtract is 4. 2 electrons per bond. You'll need to distribute the remaining electrons. How many do we have left? So we had 18 minus 4, so it'll be 14 left. So remember, 18 we started with, 4 that were in the picture, so 14 left. They need to go around each atom so that each atom has 8 electrons around it. So we're going to try it now. If we have enough to put 8 electrons around each atom, then we're done. If not, we've got to continue on. So 1, 2, 3, 4, 5, 6. That creates 8 electrons around this one. Remember, we're trying to get 8 electrons around everything, because 2, 4, 6 plus these 2 makes 8. Continuing on, 7, 8, 9, 10. Now we have 8 electrons around the sulfur. See, 2, 4, 6, 8. How many do I have to put in? Free dots. So free dots was 14. I have now put in 2, 4, 6, 8, 10. So I have 4 more to put in. 1, 2, 3, 4. Okay, so we find that we do not have enough. So you should find that you do not have enough electrons to put 8. In fact, you should be 2 electrons short. Are we 2 short? Yes. So in that case, you need to add a double bond on either side of the sulfur and draw again. So here we go. All right, so in this case, we would need to subtract how many from the total? How many bonds are in the picture now? 3. So at 2 per bond, that's 6, and that gives me 12 to distribute. So we're going to distribute them so that everything is surrounded by 8 electrons. All right, so how many do I have to put in? 12. So 1, 2, 3, 4, 5, 6. Do I have 8 around this atom? 4, 6, 8. Do I have 8 around the sulfur? 2, 4, 6. No, I need 2 more there. All right, and then on the oxygen, I need 4 more because I've got 2, 4. So 1, 2, 3, 4. Now I forgot to check. How many loose dots do we have? 12. How many have I put in? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Is there 8 around everything? 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. So yes, there's 8 around everything. So now we're finished. Now remember that the electrons repel each other, so the atoms will not be in a straight line. So if they're not in a straight line, the reason they're not in straight lines is because that pushes down on that, and that pushes down on that. So the molecule is actually going to be bent like this in a trigonal planar configuration. These bonds are polar, and so the electrons are going to pull down toward the oxygens, which makes them a negative, and then the sulfur is going to be positive, relatively speaking. And since these arrows don't cancel out, the molecule will be polar. All right, so we're going to go ahead and do this. Now we're going to look at the chart given you in class, or use the website bonding section. So here's the chart. Let me pull this in. Looks like this. So how many domains do we see in this picture? Let's go back and look at the picture again. How many places do you see electrons living? Well, there's a domain here, that's 1. There's a domain here, that's 2. And a domain here, that's 3. So it looks like 3 domains. So if there are 3 domains, look at your chart, we call that trigonal planar. So trigonal planar is the name of our domain geometry. All right, single bond. So remember that a single bond, a multiple bond, or an unshared pair of electrons count as one domain. So I think we saw 3. So 3. Since there are 3 domains, trigonal planar. Now we need to look at the molecular geometry. So I'll go back to the picture again. How many of these 3 domains? There's 2 shared. See, that's a shared domain because they're bonded. And that's a shared domain because they're bonded, but this is an unshared pair. So we have 2 shared and 1 unshared. So if you look at your picture here, or your sheet, it's trigonal planar. There are 2 shared and 1 unshared, so we call that a bent molecule. Okay, so we would say that guy is bent. And if you look at the table, the bond angles are going to be 120. Oops. There we are. So when you have 3 domains, the bond angles are 120. So the polarity of the bond is determined by subtracting electronegativity difference. If the electronegativity difference is 0 to 0.2, the bond is not polar or nonpolar. If the difference is greater than 0.2 and 1.7, the bond is polar. Now, I used 0.4 in our class this year. Sometimes you see it written as 0.2 in reference books, and sometimes 0.4. Don't get bogged down in that. You can use either one and you'll get these answers right, either 0.2 or 0.4. The bigger the difference, the more polar it is. All right, so let's go look at electronegativity values again. We have S and O. Remember, S was 2.5. Where's S? Right here. And O was 3.5. So the difference is 1. Okay, so the difference between S and O, 1. So that makes the bond polar. Okay, in a bond, electrons move toward the more electronegative element. In this case, which is the more electronegative element? Was that sulfur or was it oxygen? It was oxygen. So the negative end of the bond in each one of these cases is oxygen. So the more electronegative element will be the negative end of the bond. The less electronegative will be the positive. The negative end is oxygen. Okay, if you draw arrows toward the more electronegative element, you can determine the polarity of the molecule. If the arrows look like they cancel each other, the molecule will be nonpolar. But if they don't cancel each other, the molecule will be polar. So I'm going to redraw the shape of the molecule right here so I don't have to keep scrolling back and forth. This is what it looked like. The more electronegative element was the O. So the electrons would go in that direction and in that direction. Now if you think about these as being forces, they would push in this direction to be your overall resultant vector, and the whole thing would go down. So this guy would be pulled down if these were forces. So the point is, this arrow and this arrow do not cancel each other. In order to cancel, you'd have to go in opposite directions, but they don't do that. So they don't cancel, so the answer here is no. So since they don't cancel, the molecule will be polar. All right, I'm going to stop there, and then I'll do these this chart in just a few minutes here. Just start another movie so I don't get one that's too long.